All right, so let's run through these quickly. So to expand this, first we have a quotient, so we'll start with the quotient rule, natural log of x minus the natural log of the third root of x to the fourth plus 3. All right, here, that's the natural log of x, there's nothing to expand there, but here we have a power, really. We have a power of 1/3, right? So we have the natural log of x minus, we could write the third root as the 1/3 power. So we'll take the 1/3 down here, we'll have the natural log of x to the fourth plus 3. Now because this x to the fourth is part of an expression with 3, we can't take it down, right? And we can't have the natural log of x to the fourth plus the natural log of 3. That would only be if we had the natural log of x to the fourth times 3. Okay, we find the derivative, and we'll do so by first using these properties to expand this and take the derivative of several simpler expressions. Okay, so we have y is equal to, give it a power of 1/2, so we have 1/2 the natural log of x squared minus 4. Right, and that's as expanded as it can be. Make my pen a little smaller here. So the derivative, dy dx, is equal to a 1/2 times the derivative of the natural log. The derivative of the natural log of something is 1 over that, x squared minus 4. Chain rule says we need to multiply by the derivative of the inside, which is 2x. Okay, these can cancel out the 2, and that 2 can cancel out. So we have x over x squared minus 4. There we go. Same idea again. Let me move this out here. There we go. I'm going to expand and then take the derivative. So f of x can be rewritten as the natural log of 15x minus the natural log of x squared plus 5. And then we can rewrite this as the natural log of 15 plus the natural log of x, since we have 15 times x, minus, this one's going to stay the same. The natural log of 15 is just the exponent you would need to use on e to get 15. E to the something is 15, and that's this number. The point is, this is a constant. This is a number. And the derivative of any constant is 0, so this would be 0. The derivative of the natural log of x, that's our basic derivative of a natural log. It's 1 over x. Minus, this is very similar to the one we just did in the previous problem. Something went awry there. X squared plus 5 times 2x. The x's could, no they can't because there's subtraction there. So, find a common denominator if you want, whatever. You definitely should be able to find a common denominator and put these together because we want to be ready for the AP test. And the AP test is probably going to, if they take the derivative of something like this, going to put these together with a common denominator. All right, and I can definitely help you one-on-one if you have questions about how to do that. Find the indefinite integrals. So we are going to want to put it in terms of an integral that we know of, like the integral of something like x to a power dx, or like the sine of x dx, which of course we can't do that here, or e to the x dx, which, or e to the u du, that's definitely not that, or du over u, so a derivative over that function, a function in the denominator under its own derivative, or something close to that, right? So it looks like since I have an x squared here, and this is the power of 1, that this might be the derivative of that, or something close to the derivative of that. So if u is 2x squared plus 5, then du is 4x, just 4x dx. Okay, so if we had a 4x, and of course this dx could be written as in the numerator here. If we had a 4x dx, then we would have the derivative of this function up here, and it would look like du over u. So we'll put this 1/4 out here, of course, to balance that out. Okay, what's the antiderivative of du over u? It's the natural log of u. So here we get the antiderivative is 1/4 times the natural log of u. U is 2x squared plus 5. Absolute value, of course, plus c. If we were to take the derivative of this, we would wind up getting x over 2x squared plus 5. Write the following expression as a logarithm of a single quantity. So we're going to put these back together. Before we can combine by way of this subtraction sign, we would need to not have anything in front of the natural logs. So let's take care of that first. We'll take these and bring them up into the exponents. To the 15th power minus the natural log of x squared plus 11 to the 8th power. Now they don't have anything in front, and so because they're subtracted, we can put together these two as a natural log of a quotient of the two things. It's the 15th over x squared plus 11 to the 8th. Boom. There we go. Again, here we need to not have a 4 out in front there, so natural log of x minus natural log of x squared plus 1 to the 4th. It's subtracted, so we have natural log of x over x squared plus 1 to the 4th. Okay. Find an equation of the tangent line to the graph of this thing at point 1, 0. Okay. So imagine we have some curve, and then we have a tangent line to that curve. That's not what this graph looks like, but if we had a tangent line to the curve at some point, like 1, 0, then we want to look for the equation of this line. The equation of a line we often like to look like y equals mx plus b. So I'll kind of make a lot of room here. We like this. If we can find m and b, we are good to go. Okay, so, well, how do we find m? It means the slope of, just the slope of the line. Well, the line is the tangent line tangent to this graph at 1, 0. So find the slope means find the derivative. So y prime equals 1 over x to the 7th times 7x to the 6th. Okay? We get x to the 6th canceling with 6 of these factors of x, and so we just get 7 over x. If you think about it, I could have rewritten this as 7 natural log x, so that makes sense. The derivative of this would be 7 times 1 over x. So there we go. There's the derivative. The derivative at 1, at x equals 1, is 7 over 1 is 7, so now we know that m is 7. And now we need to know b. How will we figure out what b is? If you're not able to picture this, think about, grab my calculator, boot up apparently. Let's look at this function, y equals the natural log of x to the 7th. Let's first turn on the calculator. The natural log of x to the 7th power is, well, what's the graph look like? This is a terrible picture of this graph. Let's get a more standard view of it. There we go. So we can see the point 1, 0 is on this graph. Of course it is. Let me make this bigger. Alright, so it's asking about the equation of the tangent line right at this point. Let me grab this and I'll mark it up. So we've got this point 1, 0, and we've got this line that's tangent to that point. Right? So we're trying to figure out the equation of this line. Well, we know the y-intercept we just found was, let's see, what's going on here? We just found the y-intercept was 7. That's 7 at 1, 0. Oh, okay. I did not find the y-intercept. I don't know why I thought I did. Found the slope. Okay, the slope. Yeesh. The slope at 7. The slope was 7 over 1. Okay, so we're trying to find the y-intercept. Excuse me. That was confusing. So we're trying to find the y-intercept. Well, we don't know anything else about this line besides the slope and that it goes through this point. That's an important piece to remember. Okay. So let's zoom back in on this guy. So it goes to the point 1, 0, so we know that y is 0, the slope is 7, x is 1, and we solve for b, and b is negative 7, so y equals 7x minus 7. Find the derivative of the function, find the derivative of this guy right here. Again, it'd probably be easier if we go ahead and use the properties of logarithms. So we get x times the square root of x squared plus 15. So I'm going to do that a little bit more quickly. We've done this a few times. So I'm going to make y equal to the natural log of x plus 1/2 times the natural log of x squared plus 15. Okay, and now y prime will be the natural log of what? The derivative of the natural log of x is 1 over x plus 1/2 times the derivative of this. The derivative of this is 1 over x squared plus 15 times the derivative of x squared plus 15, which is 2x. These 2's can cancel out. We get 1 over x plus x over x squared plus 15. Alright. Locate any relative extreme and points of inflection for this function. Use graph utility to confirm your results. Okay, so y prime equals, of course, this is to find possible extrema. It's going to be, let me bring down the 13 here, it's going to cancel that 13, so we're just going to get x to the 12th minus 1 over x. Okay, we're going to want to set that to 0. X to the 12th minus 1 over x equals 0. Let's see. Let's just multiply through by x. I'll get x to the 13th minus 1 equals 0. So x equals, 13th. X equals 1. If we add 1 to both sides and take the 13th root, we'll get x is equal to 1. Okay. So then that's where we have a possible extrema. How do we figure out if it's a maximum or a minimum? Well, we could look at the derivatives and see if on the left of one, if it's positive, and then switch to the negative, or vice versa. So we could plug in values that are to the left of one and to the right of one into the derivative and see what kind of slopes we get. Or we can take the second derivative, which we're going to have to do anyway to find points of inflection. So let's take the second derivative. We'll take the derivative of that. Okay, so that becomes 12x to the 11th minus, let's see, I guess, plus 1 over x squared. Okay, because we could write this as x to the negative 1, and then we multiply by negative 1 and get positive 1, and then subtract 1 and we get negative 2. Alright, so we're going to set this equal to 0. I'll just go ahead and set that equal to 0. I'm going to multiply through by x squared, so I'm going to distribute x squared to this side, and to this side we get 0 equals 12x to the 13th plus 1. Going to, this seems crazy, we're going to subtract 1 and get 12x to the 13th equals negative 1. We're going to divide by 12. X to the 1/13th is equal to negative 1 over 12. Take the 13th root of negative 1 over 12. Okay, so at 1, what is the second derivative doing? 12x to the 11th plus 1 over x squared. Is it positive or negative? Which means if it's positive, it's concave up, and therefore this is a minimum. It's negative, it's concave down, and therefore this is a maximum. Plugging in 1, we find a 1, and 12 times 1, so 12 plus 1 is 13. So it's positive, it's concave up, so this is a minimum. All right, point of inflection at the possibly the 13th root of negative 1/12.